Good morning, one and all. Today I will discuss to find the hand movements by flexibility method of the plane jointed frame. So the flexibility method is the force method in which the unknowns are determined by the static indeterminacy. Already we know the end moments, different methods are there to find the end moments by slope deflection method, moment distribution method, energy methods, and Canis method. So among them, the matrix method is one of the method to find the end moments of the beams, trusses, frames, space frames. So the matrix method is two types, that is the flexibility method and static method. So in flexibility method we will find the unknowns in static indeterminacy. Next, the stiffness method. In this stiffness method we will find the unknowns by kinematic indeterminacy. So we will discuss the to find the end moments of the plane frame by flexibility method. The problem is to analyze the rigid jointed frame, rigid jointed plane frame as by flexible method. EA is the constant throughout. So this is the okay. So the problem is the I will run so the urea load is acting on the top. That is the 20 kilonewton per meter. Meter. So a point load is acting at the junction, that is the 20 kilonewtons. We will give the letters A, B, C, D. The length of BC is 4 meters. The length of AB is 5 meters. The length of CD is 3 meters. So you will take the same level of the D in the member BA, that is the E. Okay, this is the problem. You will find the movements. Okay, first of all you will find the unknowns. So by static indeterminacy. So the static indeterminacy is static indeterminacy is 3m plus r plus r minus J plus a. So here the rotation sum is the members, number of members. M is the number of members. How many members? 3 members. R is the number of reactions. How many reactions in each support? This is the fixed support 3. This is the hinged 2. 3 plus 2. So this is the 5. J is the number of joints. How many joints? At A, at B, at C and at D. That is the 4 joints. So A is the number of additional equations due to internal hinge. So here in this frame there is no internal hinge. A equal to 0. A equal to 0. Okay. The highest static indeterminacy is according to that equation 3 into 3 plus R 5 plus minus minus 3 into J. What is the J? 4. 3 into 4 plus A 0. So IS equal to, this will be equal to 2. So the static indeterminacy is 2. So we have 2 unknowns. So these 2 unknowns we will place at point D. So that is the 2 reactions you will place at the point D. So we have 2 redundants at point D. This is the R1, you will give R1. This is the R2, 2 redundants. kilonewton meter. This is the 20 kilonewtons. So this is the A, B, C, D. So let us assume the horizontal and vertical reactions at support D as a redundant. That is the matrix, reaction matrix R equal to R matrix of R1, R2. This is also written VD and HD, matrix of VD and HD. The vertical reaction at D and horizontal reaction at D. Okay, now you will find the moments of the each segment. Before that, we will make this frame as a determinate frame. So you will remove the redundants and find the moments according to given loads, and according to unit load you will give the R1 equal to 1 and R2 equal to 1. You will give the unit load R1 equal to 1, R2 equal to 2 to find the moments, and after that flexibility coefficients. Okay, so you will take the each segment and find the moment at a distance from the origin point due to external load and unit load at R1 and R2. So that is, so you will draw the table segment origin limit next moment due to external load, that is the big M, next due to the moment due to unit load at R1, that is the smaller M1, next moment due to unit load at R2, that is the smaller M2. Okay, first you will see, so you will see the member DC segment. So you will find the moment at a distance of some distance from the D, point D, that is say the distance you will say X. Okay, now you will find the moment at this point. Okay, now you will see the moment due to external load. There is no any external load acting on the segment DC. So segment DC origin you will give the D, point D, limit 0 to 3. Okay, so moment due to external load, there is no any load on the member, so this is the 0. So M1 also 0. The unit load will be, the R1 will be passing through DC. So M1 equal to 0. M2, so you will see M2 equal to unit load unit load acting at R2, that is the 1 into X, direction minus. So anti-clockwise direction, so you will take the anti-clockwise direction negative, clockwise direction positive. So minus 1 into X. This is the minus X. Okay. Next, segment CB. CB. So origin C, limit the distance 0 to 4. 0 to 4. So you will see the segment CB. Say you will take some distance from the C, that is the X. That is the X, and find the moments due to external loads and due to unit load. Okay, first of all, due to external load. So the external load, some external load will be acting on the CB member, that is the 20 kN per meter, and the moment is 20 into X into S square by 2. So clockwise direction positive. So 20 into X by 2, 20 into X into X by 2. X by 2. So this is the positive clockwise direction. So this is the 10 S square. S square. Okay, next M1 due to R1. So you will see. So R1 into X, anti-clockwise direction. So minus 1 into X. So this is the minus X. Next, due to R2. So R2 into the distance 3. The distance 3. So this is also anti-clockwise direction. So you will take the negative sign. So minus 1 into 3. So this is the minus 3. Next we will take the segment CE. Origin, BE, origin B. So limit 0 to 3. 0 to 3. Okay, now you will calculate the moments. First, due to external load. So you will say, so suppose this is the point. This is the E point. Okay, now you will take some distance from B, that is the X. Now you will find the moment due to external load. What is the external load? 20 kN and 20. So due to 20 kN, the moment 20 into 4 into 2. Next 20 kN, 20 into X. 20 into X. Both are 20 into X. This is the the clockwise direction. This is also clockwise direction. So you will write down So 20 plus 20 into plus 20 into 4 into 2 plus 20 into x plus 20 into x. So this is the 160 plus 20x. 160 plus 20x. Okay, next due to unit load of R1. What is the unit load? 1 into the moment. You will see the moment. So 1 into 4. 1 into this is the 4. 1 into 4, that is the anti-clockwise direction, minus. So this is the minus 4. Minus 4. Next, moment due to R2. So what is the R2? We'll see R2. So 1 into 3 minus x. This distance 3 minus x. So this is also anti-clockwise direction, minus 1 into minus 1 into 3 minus x. So this is the x minus 3. X minus x minus 3. Next segment EA. So origin is the E. So limit 0 to 2. Okay, now you will find the moments at some distance x from E. So this is the here. This is the x. Okay, now you will find the moments. First load 20 into 4 into 2 plus 20 into 3 plus x. This is the also 20 into 4 into 2, that is the 160. 160 plus 20 into 3 plus x. This is the moment due to actional load. Next, the moment due to R1. So you will see the R1 1 into 4. This is also anti-clockwise direction. So same minus 1 into 4. So minus 4. Minus 4. Next, the moment due to R2. So what is the R2? R2 into x. R2 into x. So this is the clockwise direction, positive value. So plus R2 is 1 1 into x. So this is the plus x. Okay, you will find the moments of all the segments. Okay, next you will find the displacements due to movements. So displacement due to given load, displacement displacement due to given load. Given load, that is delta will represented by delta 01 will be equal to integration of m into m1 dx by EI by EI. So you will see the m into m1, the moments in the table, delta 01 equal to first segment 0 to 3. Take the common EI. Take the common EI. EI. So M1 is 0, big M1 is 0, small M1 is also 0, 0, 0 dx plus next segment 0 to 4. See the moments m and m1, 10s square minus x. Ten s square into minus x dx. Next segment 0 to 3. See m and m1, 160 plus 20x minus 4. Plus 160 plus 20x minus 4 dx. Okay, next segment 0 to 2, integration of 0 to 2. So you will see the moments 160 plus 20 into 3 plus x into minus 4. 160 plus 20 into 3 plus x minus into minus 4 minus 4 dx. So this is the equation for delta 0 1. So you will simplify this equation, you will get minus 4840 by EI by EI. This is the delta 0 1 at R1. Next, delta 0 2 in the direction of R2. This is also that is integration m into m2 dx by EI. Same as above, you will take the moments m and m2. So you will take the common EI integration 0 to 3. So m1 equal to 0, big M equal to 0, m2, what is the m2? Minus x, totally 0, minus x dx plus next segment 0 to 3. So m1 160 plus 20x into m2. What is the m2? Minus 3. Sorry, the segment BE. Okay. This is the segment B 120 plus 20x x minus 3 into dx plus the segment BC integration 0 to 4. So m1 10s square into m2. What is the m2? Minus 3. Minus 3 dx. Next, last segment integration plus 0 to 2 into 160 plus 20 into 3 plus x into what is the m2 plus x into x dx. So you will solve this equation, you will get delta 0 to equal to minus 956 minus 956.67 by EI. Okay, this is the displacement due to external load at R1 and R2. Okay, next due to unit load in the direction of redundant R1, due to unit load due to unit load due to unit load in direction of redundant R1. Direction of redundant R1. So this is, you will write down F11. So what is the F11 means? The displacement at 1 due to unit load at 1. Displacement at 1 due to unit load at 1. Unit load at 1, that is the F11 equal to integration of m1 into m1 into m1 dx by EI. Already you know m1 values, so that is F11 equal to take the common 1 by EI integration 0 to 3 0 to 3 0 m1 in segment first segment 0. So this is the 0 whole square dx plus integration 0 to 4. This is the BC segment. So m1 minus x. So this is the minus x whole square dx. Next segment 0 to 3. Now the m1 is minus 4. See, m1 is minus 4. So minus 4 whole square into dx plus 0 to 2, the segment A, this is also minus 4. So minus 4 whole square into dx. So you will simplify this equation. You will get f11 equal to 101.33 by EI. Next, F21, the flexibility coefficient. F21 means displacement at 2 due to unit load at 1. The displacement displacement at 2 due to unit load at 1. So equal to integration m1 m1 m2 m1 m2 into dx by EI. m1 m2 into dx by EI, that is, so f11 equal to f21 equal to take the common 1 by ei. So integration 0 to 3 so m1 0 0 m2 minus 1 dx plus integration 0 to 4 m1 minus x m2 minus 3 plus 0 to 3 plus 0 to 3 m1 minus 4 minus 4 into x minus 3 dx plus integration 0 to 2 minus 4 this is the m1 what is the m2 plus x dx so this value we will get 34 by ei okay next due to unit load in the direction of redundant R2 due to unit load due to unit load in the direction of R2 so F12 the flexibility coefficient F12 this is also equal to F21 this is 34 by EI. Okay, next. Same, due to unit load in the direction of R2, so you will calculate the F22, flexibility coefficient F22 equal to integration M2 into M2 by EI into dx. So you will take the common value 1 by EI so integration 0 to 3. So what is the M2? minus 3 whole square minus 3 dx minus 3 whole square M2 into M2 minus 3 dx whole square plus integration 0 to 4 so this is not minus 3, this is the minus x into minus x whole square into dx. Next segment 0 to 4 minus 3, this is the minus 3 the whole square dx plus 0 to 3 integration x minus 3 whole square dx plus integration 0 to 2 so M2 is x, so x square dx okay. So you will solve this equation, we will get the value .56 67 by EI 56.67 by EI. So these are the flexibility coefficients. So now we will set up the compatibility equation as there are two redundants R1 and R2. That is the compatibility equation is F11 R1 plus F12 R2 plus delta 01 equal to delta 1. This is the total deflection. Next, F F21 R1 plus F22 R2 plus delta 02 equal to delta 1. These are the compatibility equations. So these you will convert this compatibility equation into matrix form. So here, so that is here delta 1 and delta 2 is 0, as the support D is as restrained, delta 1 and delta 2 equal to 0. This will be written F11 R1 plus F12 R2 equal to minus delta 01, same as F21 R1 plus F22 R2 equal to minus delta 02. Now you will convert these equations into matrix form, that is F11 F12 F21 F22 into matrix of R1 R2 R1 R2, so equal to matrix of minus delta 01 minus delta 02. So now we will put the values of these F11. What is the F11? So 101.33 by EI. So you will take the common 1 by EI, 1 by EI into matrix of 101.33 this is the 34 this is also 34 this is the 56.67 into VD into HD, that is the R1 R2 equal to minus of matrix minus of minus 4840 by EI and minus of minus 956 by EI. So to find these equations, you will get VD equal to (52.27 kilonewton of force and HD equal to minus 14.74 kilonewtons. So this is the minus 1 will be the left hand direction. So these are the reactions we will find by flexibility method. So after that we will calculate the end moments easily, whenever you will get the reactions. Okay, thank you.